At any rate, the point is that the idea is that if you measure in the given direction, if Alice measures her qubit, she may get either spin up or spin down. But if she gets spin up, then the state collapses, as one usually says, into one where were Bob to measure his qubit, he would also see spin up. And similarly, if Alice were to get spin down, then Bob would only see spin down. And this is even though Alice and Bob may be far apart from each other. So this is the non-locality of the quantum mechanics. It's what Einstein famously referred to as spooky action at a distance. How can it be for the world to be this way? Well, we don't really know, but we know that it is, because there's been now experiments for the last 30 years, I mean, more and more conclusively showing that things are exactly this way. Technically, the fact that we get these correlated states in the formalism of quantum mechanics arises from the fact that we combine systems using the tensor product of Hilbert spaces. So typical elements look like this. So they're not just pairs of states of the component systems, but superpositions or linear combinations of these things. And of course, some of these coefficients can go to 0, and hence we can get highly correlated states, even though the components may be space-like separate. And the point of Bell's theorem is that quantum mechanics is essentially non-local. There's no local description of quantum mechanics. Actually, we've already proved Bell's theorem in a couple of forms. The Bell table we had earlier gives that. I mean, the point is that that can be realized in quantum mechanics using qubits, and similarly the Hardy table, which we see again here. So the point is that this model can be physically realized in quantum mechanics, which is to say there is an entangled state of 2 qubits, and there are directions for spin measurements corresponding to these labels A1, A2 for Alice, B1, B2 for Bob, which generate exactly this table, or table satisfying these constraints, according to the predictions of quantum mechanics. And it's not just the predictions, of course, but extensive experimental verification. So this is really how the world is, like it or not. It has these features. And so the fact that this is true, as we've said, proves a strong version of Bell's theorem where we don't even need to write probabilities and inequalities to see an incompatibility with a local or non-contextual description of things. Okay, so what I'd like to do now is to show you a kind of topological way of understanding this phenomenon of contextuality, where it becomes very apparent that it's sort of about obstructing a passage from local to global information. So here is the Hardy model again. I'm now putting ticks and crosses instead of 1s and 0s, but you see it's exactly the same table. And I want to show you a way of depicting it, where we see that it's a kind of bundle in the topological sense. So here are our measurements, A prime, B prime. And we're going to put edges between these measurements to indicate measurements that can be performed together. So the idea is Alice can choose a measurement A or A prime, but not both. It's like choosing to measure spin in one direction, but then not in another, or choosing to load one bit register, but not another. But on the other hand, Bob similarly can measure B or B prime, but not both. On the other hand, Alice is here and Bob is there, so Alice can make any choice of measurement, Bob can independently make any choice of measurement, and all those combinations can happen together. So wherever there's a compatible pair of measurements, we put an edge. So this is the base space, and the possible values we can see for these variables, for each of the variables is 0 or 1, so these are the fibers over the variables. And what we're going to do is put edges between these values for the variables over edges of measurements of variables that can be measured together to indicate which are the possible joint outcomes. So you see that in the first row, all joint outcomes are possible. So we get all the possible edges we could have between these two fibers are present. But on this row here, we should only have 3, A and B prime. And indeed, you see there's only 3 edges. One of them is impossible. We can't get 0, 0, so there's no edge there. Similarly for A prime B and A prime B prime. So we can think of the, obviously this is a very simple discrete situation, but we can think of this as a kind of topological bundle where the structure of the fibers represents the values we can get for different combinations of variables that can be measured together. Now what is it, by the way, notice one interesting feature of this bundle, which is that, suppose what I might try and do is take an edge and try and extend it with another edge that's connected to form a path. Now, the first thing to notice is that there's a local property, a local consistency property, which is if I've developed a path up to a certain point, and say I'm looking at some particular edge, then on either of the incident vertices, there'll be some edge I can follow to go on from there. I can always continue a path. This is a sort of local consistency condition. As it turns out, this is the exact counterpart to a physically fundamental property of what's known as the no signaling condition in quantum information, which in terms of probability distributions is saying if you have probabilities over different but overlapping sets of variables, they have the same marginals onto the variables on which they have in common.
Sorry, they have the same?
The same marginals onto the variables that they have in common. So this is the qualitative reflection of that principle, having consistent marginals. And that's a very important condition because it says that the distribution that Alice sees on her measurements locally is not affected by Bob's choice of measurement somewhere else. If that were not the case, that would actually violate relativistic principles of causality. So although quantum mechanics is non-local, it's actually perfectly logically consistent with special relativity. And that's the local consistency that we see. So we can always extend a path. But now let's think what it means in this topological terms to have an assignment to all the variables which is consistent with the table. What it means is that we can develop a path in such a way that the path visits each vertex exactly once and then comes back back into itself. So in other words, we have a path that goes all the way around the table, assigning univocally a unique value to each variable, consistent with the constraints. Now, we can see that there is such a path in this table. This is the one shown in red. This is just a simple cycle that goes all the way around, assigns a unique value to each variable, and it is consistent with all the constraints. So such a thing does exist in this table. However, we can also ask the more refined question, is it always true if we start with some edge? That we've seen that we can always continue with another edge and another edge and another edge, but can we always continue with this global property of getting one of these nice univocal cycles that gives us a that gives us a value for each variable consistent with the table and which accounts for the edge, the possible joint outcome with which we started. And the point of the argument that we made earlier, as expressed in these topological terms, is that in general we can't. So if we start with this thing which is the starting point of our argument here, which is this edge, we can try and develop a path to account for it. So this is what we can do, following the edges that are available to us. And you see, when we go around, we don't get back where we started. We don't get a consistent assignment of values to all the variables. Okay, let's try the other way. So we can go around here, and again we don't get back where we started. And that's just a visual way, a direct visual way of seeing in topological terms the same argument that we made earlier. Now, we said that this, actually we call this kind of phenomenon logical contextuality, because we don't need to consider actual probabilities to see the issue. It actually strictly implies the probabilistic form of contextuality of the kind that we saw earlier in the Bell table. I now want to make the point that there's yet a stronger form of contextuality. And the simplest example that shows it is something that's become very important and well studied in the quantum information and foundations literature, the Popescu-Rorlich box, the PR box. This is what's shown here. Again, just with possibilities and impossibilities, the supports of the probability distributions. Now, an important difference between this table and the ones we saw earlier is that this one cannot be realized in quantum mechanics. There are more involved examples with not just 2 parties, Alice and Bob, but 3 parties or more, Alice, Bob and Charlie or more, which do realize the kind of phenomenon I'm going to show. This one is actually something that lives outside the realm of quantum mechanics, although it's still perfectly consistent with special relativity. So let's look at how this looks as a bundle diagram. So this is the table that we just saw, and here's the same kind of bundle depiction of it as what we saw earlier with the Hardy table. Now, what we see, now you can see this is a kind of discrete version of a Möbius strip, in some sense. And it's perfectly clear just looking at this, that starting from any edge in this diagram, there is no univocal path. Wherever you start from, if you keep going, I mean, it's still locally consistent, you can always extend the path, but you will never come back to the place where you started. Hopefully that's clear. And this, in fact, shows a stronger form of contextuality, which we slightly unimaginatively call strong contextuality, than what we saw earlier with the Hardy construction. The Hardy construction, there was some univocal path, as we saw, but there existed some edge locally that couldn't be extended to a univocal path. Here, there is no univocal path at all.
And univocal means only one
value for each variable. Yeah, which in terms of a path means you just go in a simple cycle and come back where you started. Now, as logicians, we might feel that there's something familiar looking about this PR box. Okay, so I mean, this is making my point that there's a hierarchy of contextuality. So one natural thing that emerges from this way of looking at it is there is sort of it's not just a one, not just an all or nothing phenomenon, but there's a hierarchy of different strengths. So there's a basic probabilistic kind of contextuality, which we saw exemplified by the Bell table. There's this intermediate form where there's some joint outcome that can't be extended, which is the Hardy construction, and then realizable in quantum mechanics, a bit more complicated and harder to draw, would be the famous construction due to Greenberg or Orman-Zeining, based on the so-called GH state, but exemplified for us by the PR. Okay, so as logicians, we might think there's something familiar looking about the PR box. Let's come to the famous example of the Liar paradox, which has been often discussed in general forms such as Liar cycles, like Liar cycles like length n, as we see here. Of course, in the n=1 case, it's just a direct self-reference. We can think of this as a family of equations which don't globally have a solution. Now, the advantage of taking a cycle is that we can see some kind of local structure here, and we can fiber the equations over the variables that they mention. And in fact, we can see that any subset of n up to n-1 of these equations is consistent, while the whole set is inconsistent. And the point now is that up to rearrangement, the Liar cycle of length 4 corresponds exactly to the PR box. It's just the same thing. So again, we see a sort of connection at the borders of paradox. And the usual reasoning to derive a contradiction from the Liar cycle corresponds precisely to the attempt to find a univocal path in the bundle diagram. So it's the usual kind of argument to formally show that this system of equations is unsatisfiable, or the set of statements like this doesn't have, can't be, I mean, either trying to set the values to true or to false doesn't work. So the usual kind of reasoning is exactly by saying, well, let's say, for example, A2 is true, and then by local propagation, which means exactly going around the path here, we end up concluding that A2 is 0. And now we say, okay, well, that didn't work, so let's suppose that A2 is 0, we go around again the second half of the path, and we come back to A2 is 1. So what we see topologically is exactly the usual argument that one follows to show that we get a contradiction. And one can take this discussion to a much broader situation. Okay, so how much time do I have? 15 minutes? 15 minutes, great. Okay, so well, so as I said before, the mathematics of this is naturally represented in a sheaf-theoretic language. I'm not going to belabor that point, but in this language, the global assignments to all the variables are global sections. And the point is we have obstructions to extending local sections to global points. So we can give a rather general definition for covering a wide range of situations, much richer than the particular cases that we've looked at, in which these notions make sense. So in particular, these sort of in this hierarchy of notions of contextuality, we could say that one of these models is logically contextual if we can't fit a local section into a compatible family, where a compatible family is exactly a sort of a family of assignments to all the variables that kind of gives us what would correspond to the natural generalization of a universal path. And it's strongly contextual if this holds for all local sections, which is exactly saying that there's no global section at all, which is a rather drastic state of affairs. There's no way of making assignments to all the variables which fits in all the constraints and hence lives in the support of the model. So I'm just showing this really to show that one can make the definitions in quite great generality. And again, just to make the point that once one's developed the sheaf-theoretic language, one can actually use some of the tools associated with that. And to me, it's a curious thing that although computer scientists have made quite an amount of use of pre-sheaves and sheaves for various kinds of semantic modeling, modeling of computations in context, it's really been done much more on the logical view of sheaves and not on the geometric view. But actually, I think a lot of this is very naturally at hand. So, in fact, well, again, I'm not going to go through the details here, but and if you do want to look at details, it's in the paper I mentioned at the beginning, and I'll give some references at the end. But we can define a suitable invariant which we can associate with each local section. And the key point is that, as we were saying earlier, there is a way of extending it to a univocal path if and only if this invariant, which we think of as defining this cohomological description of the obstruction vanishes. So if the obstruction vanishes, there's no obstruction, there is a univocal path or its natural generalization, and if not, there's a kind of witness in this non-zero element of a cohomology group. Okay. Now, the cohomology invariant isn't perfect, and this is not that surprising, although we're kind of working on getting sharper results. There are false positives, apparent ways of making these quasi-global sections, and they arise inevitably because cohomology lives in groups, and as is almost always the case, you sort of make a free group construction out of your combinatorial data in order to define your homology or cohomology groups. So there are some false positives because of when you make this formal generation of an abelian group, you get sort of funny quasi paths with negative coefficients. On the other hand, there's a very large, because everything here is quite computable, we can really compute these witnesses, and we can show that for a very large class of the, for a very large class of the examples that have been studied in the literature, in fact, it is the contextuality of these models is captured by these invariants. And we can get general results in cases where the outcomes themselves have some kind of algebraic structure. And in particular, this is important in the quantum information field because of, in fact, in the literature, many of the examples follow again an argument originally due to Berman, which may possibly show up in Ross's talk. Or what is often called all versus nothing proofs. And where these arise, and actually all the known examples in quantum mechanics of strongly contextual models do seem to have been these kind of arguments, then we can always detect these using the cohomology. So that's what this theorem here is saying. So actually, a large class of contextual phenomena are captured in cohomology, and as I say, there's still a gap in, there's a chain of implications here, and so there's certainly scope for sharper results. There's a beautiful recent paper by Robert Rausendorf, which shows that contextuality, it's one of these papers showing why contextuality seems to be a key resource in quantum computation. So this relates to the increasingly important paradigm of measurement-based quantum computing, alternative to the circuit model, which seems quite likely to be the kind of model that's actually employed in the sort of architectures that people are currently, real quantum architectures that people are currently trying to develop. What he shows is that strong contextuality, in exactly our sense, specifically using our framework, is a necessary condition in order for a particular form of this measurement-based quantum computation to be able to compute anything very strong. Otherwise, without contextuality, all you can do in this quantum computational format is essentially parity calculations. So you can't even get outside P unless you have contextuality present. So whatever is powering up, classical P, for example. And on the other hand, the measurement-based quantum computing framework is general enough to include Shor's algorithm, for example. And all the interesting things that one can do in quantum, the interesting algorithms that one can do in quantum computing. So whatever is responsible exactly for this apparent advantage over classical computing, it seems that contextuality is a key ingredient of that. Okay. And one would like to generalize that sort of result. So hopefully we can do that using this kind of machine. Okay, so I'd like to end up by connecting back to classical computer science. Because as I said at the beginning, contextuality forces itself on our attention in quantum mechanics, but once we've analyzed it in some generality, we can find that it's quite a familiar friend, which is around in many apparently more run-of-the-mill situations. And in fact, there's a sort of isomorphism between the notions we've been talking about and basic concepts in relational database theory, of all things. And this is, so relational databases, we have relation tables, remember, so we have columns with attributes, and then the table is populated with tuples, which assign values to each of the attributes in the table. There's a scheme for the database that tells you which kind of tables you have with which attributes. So, in fact, there's an isomorphism between the kind of models we've been discussing, where we just looked at possibilities rather than probabilities, for example, and with a small change of perspective, we can turn them into relational databases, and indeed, well, essentially vice versa. So we're going to think of the measurement settings, the variables as attributes in the database sense. We're going to think of the outcomes of the measurements as the data values. We're going to think of the joint outcomes as the tuples, which populate relation tables. So the Hardy model, which we wrote like this, well, if you think of each row as a little table, it turns into a little database of 4 tables. Right? So first table has these attributes and these 4 tuples, because the first row here has all 1s. And the second one has 3 tuples, because this one has 3 1s and a 0, and similarly for the other. So this is a little relational database. And of course, it doesn't have, the values don't have to be 0 and 1, they could be from any set. Okay, so once we see this isomorphism, the following question becomes rather inescapable. What is the database property corresponding to the presence of contextuality in the Hardy table? Did it escape the attention of all those clever people working on database theory? Well, in fact, it certainly didn't. There was a classic debate that raged in the database community in the late 70s and early 80s, and well remembered by people like Moshe Vardi, who participated very actively in it at the time, which was about the so-called universal relation assumption. So what was considered as whether, and the debate was about, is it reasonable to assume, if a given relational database is a kind of global consistency condition, that at least in principle there's some big table in all the attributes, some big table up in the sky, which would give you back all the little tables by projection. That's the universal relation assumption. And what the contextuality of the Hardy table is telling us is that in this very simple example, we already see that there's no universal relation possible for this little database. And by the way, the conclusion of this debate, after a lot of controversy, and there are many classic papers on this, was that it's not reasonable to impose the universal relation assumption. Which is an interesting point. I mean, all our records and salaries and goodness knows what are in databases, this more or less of this kind of form, and the universal relation assumption isn't imposed. So we must assume that in those very big databases that our records are in, there probably are instances of contextuality of this kind. So what does that mean, actually? Not entirely sure, but it's an interesting point. So again, local consistency, but not global consistency. And so we get a sort of dictionary of notions here, which goes quite deep, actually, deeper than what I've discussed. There's a beautiful result by Vorobyov from around 1960, actually coming from yet a different source. He was sort of a founding figure of a Soviet school of game theory of that era. And he proved a beautiful result, which in our language amounts to this. If you have a family of probability distributions, which you think of as on exactly the sort of sets of variables as we've been describing, which have this property of having consistent marginals, can we give combinatorial conditions on the, you can think of these sets of variables as expanded under subset to an abstract simplicial complex. It's an equivalent way of thinking about things. Could we give combinatorial conditions on this, which guarantee that we can always, for any such family of distributions, find a joint distribution, which would marginalize to give you all of these things, which you can see is the probabilistic version of is there a universal relation? Is there a joint distribution? And he actually gave, in his beautiful result, necessary and sufficient conditions on the combinatorial structure of the complex for such a joint distribution to arise. And actually, the conditions he gave, although not expressed in the same form, can be seen to be equivalent to the well-studied notion of acyclicity of database schemes. So database schemes, no thought of probability in the way they're usually formulated, but the combinatorial condition in any of the sort of 6 or 7 usual formulations is equivalent to the one that Vorobyov gave in his setting. Okay. So why do similar structures arise in such different settings? Well, I think because understood in this fashion, contextuality is indeed a pervasive phenomenon. And we can already see quite a lot of results that go in this fashion, including results relating to constraint satisfaction, which I haven't had time to talk about. So let me just finish up by mentioning, well, I've had the pleasure of working with many colleagues on these topics. In particular, one of the ideas originated and continue in joint work with Abramsky, the ideas about the logical way of deriving Bell inequalities in joint work with Lucian Hardy, the same Hardy of the Hardy paradox. And yeah, there are lots of interesting things going on in this field, I think, and a lot of things that can, I think, are attractive for computer scientists and for this kind of community. This is too much fun, far too much fun to leave to the physicists, but actually I think it addresses fundamental issues, makes us rethink fundamental issues about the nature of information processing, which are certainly worthy of our attention. So I'll just finish up with a few references if you want to find further details for some of the things I've been talking about. Okay, thanks very much.
We're running into a break, but of course we have time for observations, questions.
Is linguistic contextuality in any way related to what you have talked about? Or is it something entirely different?
Well, I've done a bit of work on applying this kind of structure to anaphora. If that's, when you say, so that would be an example, where again you're sort of looking at, so you're looking at ways of, yes, I mean, I think there is a useful connection, although, you know, at the moment there's just been some initial consideration of that. But yes, it is obviously a compelling example of clearly contextual phenomena.
Back?
Samson, statistical databases became a big thing with the growth of differential privacy. Have you looked at applying contextuality in the context of statistical databases?
Not yet, no. If you explain, I've learned, yeah, I agree. Nowadays, probability in databases are increasingly probability is becoming increasingly important in the world of databases. Yeah, it sounds like a good idea. I haven't thought of that.
It would be interesting to have an example from machine translation of a sentence, which when you translate it repeatedly from Russian to English and back again through a cycle of languages, choosing in every case the best justified idiomatic translation.
Yes.
You get that negation of your original sentence.
Could you have
I
examples?
don't have one actually like that.
Yes.
I don't think I know enough languages.
I think there will be kind of examples that are quite striking of this kind, but yes, it's...
So it's a normal, very common case of inconsistent preference cycles.
Yes, well, preferences is, yes, so indeed, actually, there's already been some work by a couple of students in the group at Oxford on looking at, this structure fits very naturally with the theory of preferences of individual preferences as developed by Samson and others in economics. So yes, that's exactly the sort of situation